Now we finish chapter 15, complex numbers, looking specifically at complex numbers. We looked at the foundations of what makes up the imaginary numbers and our J operator, and in looking at how we handle some of those values. Now let's look at complex numbers as combinations of real and imaginary numbers. So in our first example here, we're going back to our square root of 36 and negative square root of 36 example, where we have a positive and a negative. So we can see now when we operate on these square root values, we end up with two terms, real and imaginary. So in this case, since the square root of 36 simply becomes 6, and we've seen now that the square root of 36 becomes 6 and the square root of minus 1, which we use the J operator, we end up with our first real complex number with a real number and an imaginary number. So hopefully when you look at this, you get an idea of what this is going to look like on the graph now. You're going to end up with a point at 6 and a point at J6 up in that first quadrant that will give you a vector then to that point from the origin 0 out to 6 and J6. In the next example, we've added a little more complexity in that we've got a J squared, and a J cubed. So in this case, we should be getting familiar with that. The J squared yields a negative number, and the J disappears, and that a J cubed then gives us a negative J in this case with the 2 left over. So now when we have a J6 and a negative J2, we can combine those terms. You can only combine J terms and real terms. You cannot intermix them. So we end up with minus 12 plus 4. Okay, so here's that graphical representation. In looking at a graph then, if we have two complex numbers, 2 plus J4, minus 4 minus J6, you can see how they plot. These red arrows actually become the vector. So if we choose our plot as 2 on the real, J4 on the imaginary, and we put a dot there, and then we draw a vector or a radius, in some cases from 0 out to that point, we have created then the graphical representation of that complex number. The same thing for minus 4 minus J6. When we plot this out, minus 4 on the x-axis, minus J6 on the y-axis, we have a point right here. Again, we draw our vector out to that point. So vectorially, now what we're looking at are those vectors that are formed by the complex number relationship. And one other thing that you need to start thinking about is the fact that really what we end up with here are two projections. We've got a projection of 2 units on the real axis and a projection of 4 units on the imaginary axis. In this case, we've got a projection of 4 units onto the x-axis, a projection of 6 units onto the y-axis. So now, how do we handle adding, subtracting, multiplying, and dividing complex numbers? Well, to add or subtract complex numbers, first add or subtract the real parts, and then add or subtract the imaginary parts. Again, you cannot mix them up because they are 2 separate components now that you see on the x and y axis, but you can treat them by their likeness. So if we have 6 plus J3, 4 minus J7, and we just set them up like a normal addition problem, we've got all of the real components here to the left, all the imaginary components to the right, and that's generally the way you set it up. And do your addition, I can add minus 7 and 3 together. I end up with minus 4. I can add 6 and 4 together, and I get 10. So that's as far as you can take it. You cannot combine any of the real and the imaginary points beyond that. Now, if I want to take the difference then and do a subtraction, Again, put them together just like you would for a subtraction problem. 25 plus J16 minus 15 plus J12. When I combine the imaginary terms, I get a minus J28 and I get a minus 40. Why is that? Because this negative sign here that we had, that we normalized. Negative times a negative is a positive, and a negative times a positive is a negative. So we treated the sign difference as we went through here, so that we ended up with a 16, 12 gives us 28, but it inherits this negative value. And then 15 and 25 then end up becoming the sum when these signs inherit. For multiplication, almost like addition, we multiply the complex numbers in the same way. And we treat it just like we did before when we did some of our equations in factoring. So 2 times 2 gives us 4. 3 times 2 gives us 6. 2 times 4 gives us 8. 3 times 4 gives us 12. And the j's then become squared. So 4 plus j6 plus j8 plus j squared, 12. Then we can reduce our like terms. We're going to gather our terms together. 6 and 8 give us 14. J squared gives us a negative number, so we end up with a negative 12 and 4. So when we combine negative 12 and 4, we get a negative 8 plus J 14. So the handling of a multiplication is fairly easy. Now, division is a different story. Division is different because we have to do something called the complex conjugate. We have to take a conjugate of the denominator and do something like we do when we went through and did our common denominators. So for division, we divide complex numbers. We multiply the numerator and the denominator by the conjugate or the complex conjugate of the numerator. This will remove the imaginary part of the denominator. That complex conjugate is the same number, but we change the sign of only the imaginary part. So the conjugate of 2 plus j3 is 2 minus j3, and 4 minus j5 is 4 plus j5. So let's look at an example. We're going to divide these two expressions, 2 plus j3 divided by 4 minus j6. So you can see here when we set this up, there's our normal division. The next thing that we have to do is multiply the denominator and the numerator both by the complex conjugate of 4j6. So 4 plus j6, numerator and denominator. Again, just treat each term. 2 times 4, 3 times 4, 2 times 6, 3 times 6, j squared. And so down here you can see we've got all of those expansions that have occurred in the numerator and the denominator. What that complex conjugate, though, has done was eliminated the j in the denominator, and that's something that we usually always try to do. We try to get rid of that j in the denominator. So when we do this, you can see we have plus 24 minus 24. Those cancel out. The j squared becomes a negative value on the 36. So now we have 16 and 36 that we've added together to give us 52. Okay, now we can separate these out. 10 over 52, 24 by 52, and run it through your calculator. 52 into 10 goes 0.192. 52 into 24 goes 0.462. And you are done. Again, you cannot combine these. So take some time, learn this process of the complex conjugate, and do some exercise problems so that you get a good handle on doing the division. So the division process is just a little different than all the others because we have that extra conjugate step. So that gets us through complex numbers. Now you understand the right triangle and complex numbers, imaginary numbers, and what the graphing looks like. And we will proceed as we go forward then, applying this to the AC circuits with capacitors and inductance and reactances.